In this part 2 video, I'll be solving two more questions from exercise 13.1 and then we move on to next exercise 13.2. And the first question that I have taken here is question number 12, and the question is, assume that each born child is equally likely to be a boy or a girl. If a family has two children, what is the conditional probability that both are girls given that number 1, the youngest is a girl, and number 2, at least one is a girl. So according to this question, a family has two children and we don't know whether the two children are girl or a boy. Now let us represent a boy child by B and a girl child by G. Then first we need to find the number of elements in the sample space, which is given by S equals to B comma B, B comma G, G comma B and G comma G. So it means that there are 4 elements in the sample space. So first represents that both the children are boy, and the second represents that first is a boy child and second is a girl child. So youngest is girl here, and here first is girl child and then boy child. So youngest is a boy child and here both are girls. Now let E be the event such that both the children are girl child. So out of 4 elements in the sample space, only one contains G comma G, which represents that both the children are girl child. So in the set E, there will be only one element, which is G comma G. And let F be the event such that the youngest is a girl child. So youngest is a girl child means the second child must be a girl. Here there is one and here there is another. So altogether there are 2 elements in the set F, which is B comma G and G comma G. In both the set E and F, only one element was common. So here we write E intersection F equals to G comma G. So which is the common element in the set E and F. Then we write the probability of the event F. So PF equals to the number of elements in the set F was 2 divided by the number of elements in the sample space is 4. So 2 divided by 4. And similarly, P E intersection F equals to 1 by 4. Because there is only one element in the set E intersection F and the total number of elements in the sample space is 4. And then we find the conditional probability that both are girls given that the youngest is a girl. And it is represented by P E by F. So this is the formula, P E by F equals to P E intersection F divided by P F. So using this value here, and after simplification, we will get 1 by 2. So the probability is half. Now let us solve the second part of the question. And the question says that at least one child is a girl. So let us represent this event by F. So F is an event such that at least one child is a girl. So out of the 4 elements in the sample space here, so except this first element B comma B, the rest of the 3 elements contains at least one G. So which means that at least one child is a girl. So altogether there are 3 elements in the set F. And then we find E intersection F. So in the set E and set F, only one element, which is G comma G, is common. So we write E intersection F equals to G comma G. And then we write the probability of an event F, which is given by PF equals to number of elements in the set F is 3 divided by total number of elements in the sample space is 4. And similarly, we find PE intersection F equals to 1 by 4. Therefore, the conditional probability that both are girls given that at least one child is a girl is given by PE intersection F, and this is the formula. And after replacing the value here, and after simplification, we will get 1 by 3. Now let me solve question number 15, and the question is, consider the experiment of throwing a die. If a multiple of 3 comes up, throw the die again, and if any other number comes, toss a coin. Find the conditional probability of an event that the coin shows a tail, given that at least one die shows a 3. So according to this question, we need to throw a die first. So in a die there are 6 numbers from 1 to 6, and the multiple of 3 is 3 and 6. So altogether there are 2 numbers which are multiple of 3. And if the multiple of 3 comes, then we have to throw the die again. And again there is a chance of getting a number from 1 to 6. But except these 3 and 6, if any other numbers like 1, 2, 4 and 5 comes, then we need to toss a coin instead of a die. So here there is a die and a coin. Then first we need to find the number of elements in the sample space. So these are the number of elements in the sample space. So if 1 comes in the first row, then according to the question we have to throw a coin. So in a coin there is either head or tail. So if we get 1 in the die, then in the second row we will get either head or tail. And similarly, if we get 2, 4 and 5 in the first row, then in the second row we have to toss a coin. So we will get either head or tail. And if it comes the multiple of 3, like 3 and 6, then we have to throw the dice again. So here in the first row we have got 3. In the second row also we have to throw a die. So there is a chance of getting a number from 1 to 6. And similarly, if we get 6 in the first row, then in the second row there is a chance of getting a number from 1 to 6. So altogether here there are 20 elements in the set. Now let us represent an event E such that the coin shows a tail. So out of these 20 elements in the sample space, so how many elements contains T? So here there is 1, this is the second, third, fourth. So there are altogether 4 elements in the sample space which contains at least 1 T. So there are 4 elements in the set E. And similarly, let us represent an event by F which denotes at least one of the dice shows 3. So out of 20 elements in the sample space, how many contains 3? So we have to look for it. So here there is 1, second, third, fourth, fifth, sixth, and here 7. So altogether there are 7 elements in the set F. Then we need to find E intersection F. So if we look at in the set E and set F, we find none of the element common. So E intersection F is a null set, so which is represented by 5. Then the probability E intersection F equals to 0. Then we find the conditional probability that the coin shows a tail given that at least one die shows 3 and is given by PE by F. So by using this formula and putting the above value, we'll get 0 by PF, which is 0. So this is the answer for question number 15. After solving exercise 13.1, where we have solved the problems related to the basic probability and conditional probability, now we move on to the next topic of the chapter probability, so which is multiplication theorem on probability. If E and F be the two events associated with the sample space, and the simultaneous occurrence of both the events is represented by E intersection F, or simply we can write EF. And the probability of the event E intersection F or EF is given by the product of probability of the event F multiplied by the conditional probability of an event E where the event F has already occurred. Or there is another formula also, which is the product of the probability of the event E multiplied by the conditional probability of an event F where the event E has already occurred. And this rule is known as multiplication rule of probability. So this is the main formula. Now let us define independent events. If E and F are two events such that the probability of occurrence of one of them is not affected by the occurrence of the other, such events are called independent events. So here, if we consider two events E and F, which are not dependent on one another, so that means they are purely independent of one another, so that event we call it independent events. And the formula for the independent event is P E intersection F equals to the product of probability of each of the event, that is PE into PF. So if we consider three events A, B, C, then P A intersection B intersection C equals to PA into PB into PC. So which is the product of probability of the three events, and if the events are not independent events, then this formula will not hold. So for an mutually dependent events, P E intersection F is not equals to PE into PF. So this should be kept in mind. So we can use this formula only if the events are independent to one another. Now let me solve question number 3 of exercise 13.2, and the question is, a box of oranges is inspected by examining 3 randomly selected oranges drawn without replacement. If all the 3 oranges are good, the box is approved for sale, otherwise it is rejected. Find the probability that the box containing 15 oranges out of 12 are good and 3 are bad one will be approved for sale. So in a box there are 15 oranges, and out of 15 the 12 oranges are good and 3 are bad. And we need to take out 3 oranges one after another without replacing back. Let A, B and C be the respective events that the first, second and the third drawn orange is good. So according to question, there are altogether 15 oranges out of which 12 are good. Now let us think that the first orange that we draw from the box is good, and the probability of getting the first orange good is represented by PA and is 12 upon 15. According to question, we are not allowed to replace the orange back to the box. So one orange we have already taken out. The remaining will be 14, out of which 11 are good now. Then the probability of getting the second orange good is represented by PB, which equals to 11 by 14. Till now we have taken out already 2 oranges from the box. So remaining is 13, out of which 10 are good. Then the probability of getting the third orange good is represented by PC, which equals to 10 by 13. Since the three events A, B and C are mutually independent, therefore the probability of getting all the oranges good is given by PA into PB into PC. So after replacing the value and simplification, we'll get 44 by 91. Thus, the probability that the box is approved for sale is 44 by 91. So this is how we solve question number 3. Now let me solve question number 7 of exercise 13.2, and the question is, given that the events A and B are such that PA equals to half, PA union B equals to 3 by 5 and PB equals to P. Find P if they are mutually exclusive and independent. So first we consider when A and B are mutually exclusive. So if they are mutually exclusive, then A intersection B will be a null set. So then the probability of an event represented by A intersection B will be 0, because there is no elements in the set A intersection B. And we know the formula PA union B equals to PA plus PB minus PA intersection B. So after replacing the value of PA, which is half, PA union B, which is 3 by 5, and PB equals to P, and PA intersection B is 0 here. And after simplification, we'll get the value of P, which is 1 by 10. Now when A and B are independent events, then first we find PA intersection B, which is given by the formula for independent events, PA into PB. So PA is half and PB is P. So that after replacing the value, we will get PA intersection B equals to P by 2. And then we use the formula PA union B equals to PA plus PB minus PA intersection B. So after replacing the value here and after simplification, we will get P equals to 1 by 5. Now at last let me solve question number 8, and the question is, let A and B be an independent events with PA equals to 0.3 and PB equals to 0.4. Find PA intersection B, number 2 PA union B, number 3 PA by B, and number 4 PB by A. So first we need to find PA intersection B. So for an independent event A and B, the formula is PA into PB. So after replacing the value of PA and PB here, and after multiplying, we will get 0.12. So which is the value for PA intersection B. And then we need to find PA union B. So this PA union B is given by the formula PA plus PB minus PA intersection B. So PA is 0.3, PB is 0.4, and PA intersection B is 0.12. So after replacing the value here, and then after simplification, we have got 0.58. Now let us find PA by B, which is given by the formula PA intersection B by PB. So PA intersection B we have already found out, which is 0.12, and PB is 0.4. So after putting the value and after simplification, we will get 0.3. And similarly, we will find PB by A, which is given by the formula PA intersection B by PA. PA intersection B is 0.12 and PA is 0.3. After replacing the value and after simplification, we will get 0.4.